Okay, now let's talk about the equilibrium constant. And I just want to show you where the equilibrium constant comes from. You don't need to reproduce this because it's some calculus and thermodynamics that you haven't had yet, maybe. So let's consider the Gibbs free energy, which you will learn about later in the semester. And we can write the change in the Gibbs free energy in terms of the pressure and the temperature. And if we impose constant temperature, then the change in temperature is 0. And so we only have a pressure dependence upon the Gibbs free energy. So this is a way for us to correct the Gibbs free energy for a change in pressure. So now we'll use the ideal gas law and substitute in for V. So we have nRT over P. So that's the volume from the ideal gas. And now we assumed constant temperature, and we can integrate both sides of the equation, and nRT is a constant which we can take out of the integral. So we'll get delta G is equal to nRT natural log P over P standard. And we're going to integrate from P standard, 1 atmosphere, to some pressure. So this is a way to correct G from 1 atmosphere to some other pressure. So now we have this expression, and we can, from the identities of lateral logarithms, we can take this n coefficient and put it as a power in the argument of the log. So we have this expression. So this corrects the Gibbs free energy to a non-standard pressure, some pressure besides 1 atmosphere. Now if we did this for a whole reaction, we would get this, where we can combine all the natural log terms. And this right here is called the equilibrium constant. So I wanted you to know where it comes from. It comes from correcting a gas at different pressure for delta G, the Gibbs free energy. So now let's look at how we can practically use the equilibrium constant. So say we have a reaction and we want to express the equilibrium constant for this reaction. And I use this sub P to show it's in terms of pressure, because in that expression we had, it was the pressures of the species. So it is the pressure of the products divided by the reactants, because in delta G reaction, it's products minus reactants. And so in that natural log term, we would have the natural log of the products minus the natural log of the reactants. And so the coefficients, when we combine the log terms into a product, then the reactants will be in the denominator. So we have the pressure of the products divided by their standard pressure raised to their stoichiometric coefficients divided by the pressure of the reactants raised to their stoichiometric coefficients. So that's the equilibrium constant for this particular reaction, and that's complicated. So you'll notice one thing, that I have pressure over pressure. This is pressure standard, so this is 1 atmosphere pressure. So I'm dividing by 1 here. So I'm not changing anything numerically. I'm just dividing by a standard 1. And the units all cancel because I have pressure divided by pressure, pressure over pressure. So all the units will cancel, so the equilibrium constant is unitless. And since it's unitless and dividing by the standard pressure 1 doesn't change anything numerically, I'm going to write it abbreviated, or an easier way to write it, and I'm going to leave out the standard pressures and just realize that all the units are going to cancel even though I don't have the standard pressures here. So I'll write practically Kp, the equilibrium constant in terms of pressure, is equal to the pressure of the products raised to their powers over the pressure of the reactants raised to their powers. Now, depending on the powers of C, D, and A and B, the units might not cancel in this expression, but we're just leaving out the standard pressures because we don't want to write so much. So this is an abbreviated way of writing. Just realize that cancel all the units, K is going to be unitless. This is just an easier or abbreviated way of writing all of this. So now we have an equilibrium constant definition for a particular reaction. So what does this mean? So the equilibrium constant is just a number, and it depends upon the amounts of the reactants and products raised to their stoichiometric coefficient. So this is just going to give a number. The higher the number, since products is in the numerator, the higher the number, the greater the amount of products at equilibrium. The lower the number, the greater the amount of reactants at equilibrium.